In the last hour, I stated Benson's lemma, which is here. And from this lemma, we derived this theorem that the semi-simplification of a symmetric tensor category is, justifying its name, a semi-simple symmetric tensor category. And we describe the simple objects. They are indecomposables of C of non-zero dimension. So let me explain the proof of Benson's lemma. Prove this direction. When dimension is non-zero and F is an isomorphism, then it's not negligible. Well, in this case, we can take trace of F composed with F inverse, which is trace. So if F is from X to Y, and F inverse is from Y to X, so let me do F inverse composed with F. So this is trace of the unit of X, which is dimension of X. And that's not zero. And so this means that it's not negligible. And let's prove the other direction. So for the other direction, we want to prove that if dimension of X is zero, then any F from X to Y is negligible. F is not an isomorphism, then also it's negligible. So why is this true? Well, this is simply because for any phi from X to X, trace of phi equal to zero. And so why is that? Well, because we again recall that endomorphisms of X is K plus M, and this is a nilpotent ideal. And so every phi will be written as lambda plus M, and so this is nilpotent. Trace of phi is equal to lambda times dimension of X plus trace M. This is zero because dimension of X is zero. And trace of a nilpotent endomorphism is always zero. So because there is a filtration by kernels of powers, and in the corresponding presentation, we can write it by upper triangular matrix with zeros on the diagonal. Actually, I'm oversimplifying it. So what's important to that in any tensor category, so it's a lemma, actually not completely trivial. It's a check of good understanding of axioms of a tensor category. So in a tensor category, 0 goes to X, goes to Z, goes to Y, goes to 0 is a short exact sequence from Z such that F maps X to X. By quotienting, it defines also a morphism from Y to Y. The trace in Z of F equals to the trace on X of F plus the trace in Y of F. Using this, it is easy to show the trace of an nilpotent endomorphism is zero. For example, if you have such a short exact sequence, example of a nilpotent endomorphism is one that acts by 0 on X and then maps maps Z to X. That's a general endomorphism of order 2, nilpotency order 2. And in this case, action of F on X is 0 and action of F on Y is 0. So these are both 0, and this implies that the trace of Z. So in other words, this F is going to be something like this. And so its trace is then 0. Okay, so that case is taken care of. And then the second case is suppose that F from X to Y is not an isomorphism. Okay. Well, in this case, so first of all, suppose it has a kernel. Kernel of F equals to, I should not do this, but just say that let G. So assume F is not negligible. Then we have G from Y to X such that trace of Fg, so Fg is a map from Y to Y, and the trace of Fg equals to lambda, which is not 0. Well, I can make it 1. And then, so this implies that this composition Fg, well, Y is indecomposable, so composition Fg is 1 plus M, where M lies in the maximal ideal of end Y. And this means that F times G times 1 plus m to the minus 1 is the identity. And so this means that we have a map from y to x and then back to y such that the composition is the identity. So this means that y is a direct summand of x, but because x is indecomposable, this means that y is isomorphic to x, and f is an isomorphism. F from x to y is an isomorphism. So we use that y is indecomposable because we use that endomorphisms of y is a local algebra to represent the element this way. And we also use that x is indecomposable to say that if y is a direct summand, then x, this in fact means that y and x are the same. Okay, so this proves the part 1. Any questions? Oh. That's right. Okay, let's do 1 over the dimension of. Okay, dimension of y. Let's say, yeah, I mean, probably I should just say that, okay, I should switch the order. So G, trace of GF is dimension of X. And then GF, X 1 plus M is the identity. And this will be from X to Y to X. And so this means that X is a direct summand of Y. So this means that this is an isomorph. Both X and Y are indecomposable, and they're using both conditions. Okay, so now part 2 is also quite easy. So, well, if Fij are negligible, then for every G, which is Gji, trace of Fg is the sum over I and J, trace of Fij, Gji is 0. So this means that F is negligible. And in fact, you can reverse this argument to prove that if F is negligible, so if F is negligible, take G equals to some Gji equals to 0, Gmn equal to 0 for all m not equal I and n not equal j. And then the trace, then we will have the trace of Fg is going to be the trace of Fij Gji. And therefore, since this is always 0, this means that this must always be 0. And so Fij is okay. So this is the proof. This implies the theorem. And so what I want to do now is to apply it to consider examples. So in general, this means that we have the same. By the way, I want to mention that we didn't use anywhere that this is an abelian category. The only thing we did, the only place where we did, is that when we took this filtration by kernels of powers of a nilpotent element. But we don't need to this filtration. We can simply assume the trace of every nilpotent endomorphism is 0. So it's a remark that Benson's lemma and semi-simplification theorem for a pseudo-tensor category such that for every f x to x nilpotent endomorphism in C, trace of f equals to 0. And this is important because some important categories that we want to semi-simplify are not abelian. For example, C is the category of tilting modules over a reductive group and positive characteristics. So this is an important example, which was considered by Gelfand and Kashdan and also by Georgiev and Mathieu. And in fact, it also works, well, pivotal categories, which have a good notion of a trace. So I'm not going to get into this, but in particular, braided categories of representations of quantum groups are okay. And in particular, we can take tilting modules for a quantum group and apply this, and we will get so-called Verlinde categories, which are arise in Vesumin-Witten model of conformal field theory. And this connects to Jasper's lectures, who talked about conformal blocks. Well, some finite limits of them, but that's actually what is this related to. Anyway, so I don't want, so this is true in much wider generality, but now let's go back to just symmetric categories and positive characteristic. So of course, so this is a wonderful procedure. So this is a wonderful procedure that allows us to pass from a non-semi-simple category, which could be quite complicated, to a semi-simple one. But we pay a price that we get a lot more simple objects. Instead of, so we have irreducible objects in this new semi-simple category are indecomposable objects in the old category. So in fact, indecomposable objects of non-zero dimension, but there is still a lot of them. So if you try, for example, to take a group, something like Z3 cross Z3 in characteristic 3, and try to classify indecomposable representations, this is really a wild problem. And there is no good classification. There are lots and lots and lots of them, and they don't, you cannot parameterize them by anything nice. However, in some special cases, this category is very nice. And this is when we can describe all the indecomposable representations. So the example I'm going to take is C is representations over K of the group Z mod P, the cyclic group, where P is the characteristic of K. So then we can list indecomposable representations. Because what is this? So this group is generated by an element G, such that G to the P equals to 1. And since we work over a field of characteristic P, this equation in the group algebra can be written as G minus 1 to the P equals to 0. So this means that we're classifying nilpotent operators, which become 0 when we raise them to power P. And such operators are, of course, classified by Jordan blocks, but each Jordan block, Jordan normal forms, but the condition is that a Jordan block cannot have size bigger than P. So we have indecomposable representations, GA1, GA2, up to GAP. These are Jordan blocks. So G minus 1 acts by, and this is size n, where n varies between 1 and P. And now these are indecomposable objects, and they will become irreducible objects of our category C bar. So let us call these objects L1. There will be LP minus 1 and LP. But this LP has dimension P, so it will be thrown away and will become 0. So we have only objects from L1 to LP minus 1. And now we want to write a tensor product rule. So, so suppose you want to tensor LM with LN, with Jordan blocks of size M and N. So in characteristic 0, of course, Jordan blocks tensor in the same way as representations of SL2, because representation of SL2, the element E acts by a Jordan block. And so this is given by the Clebsch-Gordon rule. So this is a direct sum from I equals 1 to minimum Mn, L of M minus N plus 2I minus. But now in characteristic P, so in C bar, there is some truncation going on. So for example, suppose we take L3 tensor L3. Well, this rule tells us that we have to take the sum from I equals 1 to 3 of this is 0, so L2n minus 1. So it's L1 plus L3 plus L5. But now let's assume characteristic of, so let's assume that P equals to 5. Okay. Well, in this case, what happens is this L5 drops out. So the rule, so certain terms drop out. And so the rule that you actually, not only, it's not just the term divisible by P drops out, but for example, if we multiplied, so there could be some terms dropping out because like L3, L5, and L7 could drop out and something like this. So what you compute is, what you can show is that you get the same formula, but up to minimum Mn, P minus M, and P minus N of L, M minus N plus 2I minus 1. And so this is called the Verlinde rule. arises from the same categories I just mentioned, and it appeared in conformal field theory in the work of physicist Erik Verlinde. And in particular, in this case, it gives this thing. But this already shows that the Deligne theorem does not hold in characteristic phi. Because suppose we had a fiber functor f from C bar. So C bar is this category. C bar is a counterexample to this theorem, because if we had a fiber functor into super vector spaces over K, and let's say D is the dimension of F of L3. This is just ordinary vector space dimension. Well, then this equation implies that D squared equals to D plus 1. And this equation, of course, doesn't have any integer solutions. Its solution is the golden must be equal to 1 plus minus square root of 5 over 2, which is nonsense. Well, I mean, it will. So if we call this f of L3, we call it V, we will have V tensor V equals to K plus V. And there is no vector space that satisfies such condition for this reason. Okay, and then similarly, greater or equal to 5 for every P. If we had F, we can look at dimension of F of L2. So for L2 and L3 will give the same answer, but if you consider dimension F of L2, this is going to be 2Q, where Q is equal to e to the pi I over P. So this is Q plus Q inverse, or Galois conjugate. It will satisfy the minimal polynomial for this algebraic integer. And this algebraic integer is not an integer, so this will give you a contradiction. So we see that the Deligne theorem is actually false in dimension characteristic greater or equal to 5. Actually, it also fails in characteristic 2 and 3. But for 2, I will explain this. For characteristic 3, it is a little harder to see, but because your example that you have to take is non-semi-simple. Exactly, yes. So there is another construction of this category, which is, I mentioned here, that if you have the category of tilting modules for the group G, you can take it semi-simplification. And in particular, if you take SL2 in characteristic P, you will obtain the same. Well, there is only one category which has these fusion rules. So basically, also, well, in this case, your Hopf algebra has a group-like element G whose piece power is 1. But you can take a primitive element X whose piece power is 0. And so this is like additive version of this group. And you would get the same. No. So for P equals 3, so e to the pi I over 3 is equal to 1 plus square root of 3 over 2, and so this will be 1. Yes. So in fact, in that case, you will get super vector spaces. So let me actually make that formal. So definition: the Verlinde category is so it's defined over a field of characteristic P. It's the semi-simplification stations over K of Z mod P. And in fact, it is also representations over K, K of X over X to the P, the Hopf algebra with primitive element X. And it's a semi-simplification tilting category of SL2. The construction is more complicated. Okay, so now what do these categories look like for small p? Well, first of all, for p equals 2. P equals 2, we only have L1, which is the unit object. So in this case, Verlinde 2 is just vector spaces, or nothing very fancy. So in this case, we don't get a counterexample from here. Then what is Verlinde 3? So for Verlinde 3 is, well, it has L1, which is the unit, and then L2, which let me call it psi. And then this rule says that psi tensor psi is 1. Like representations of Z mod 2, But you can actually, this semi-simplification procedure, it preserves dimension for obvious reasons, because any monoidal functor preserves dimension. And psi is obtained from Jordan block of size 2 by 2, because it's L2. So that means its dimension is 2, which is characteristic 3 equals to -1. So we see that the dimension of psi equals to -1. And that means that we don't have representations of Z mod 2, but rather we have super vector space. So this is just super vector spaces. In general, take LP -1 and call it psi. Then you have psi tensor psi equals to 1. And psi represents the Jordan block of size p -1. So it has dimension p -1, which is -1. And so, this L1 and LP -1 generate a subcategory which is super vector spaces over K. And then the whole var P for P bigger than 2, the whole var P is the tensor product of var P plus box times super vector spaces over K, where this var P plus is spanned by objects with odd subscript. We have this factorization. So this is a kind of box times operation with tensor categories, and it is pretty obvious what that means, especially for semi-simple categories. Objects of this are just products of objects of simple objects of this and simple. Okay, and so in particular, this var 5 plus. So in particular, this var 5 plus is generated by L1 and L3, and this is 1, and this I could call x, for example, and then I have x tensor x equals to 1 plus x. And this is called, for obvious reasons, the Fibonacci category. I think it is not known whether Fibonacci considered it, but it is called that way. So, and now, so we've got a new category, which is a new example, which is not super Tanakian. And now, how should we proceed? Well, remember how we proceeded when we had super vector spaces, a new example compared to Tanakian category. Well, we said, okay, since it doesn't have a fiber functor into vector spaces, well, it has at least fiber functor to itself. So let's study all categories that have a fiber functor into that category. So definition, C is var P Tanakian. It admits fiber functor. And again, this means that it is exact and monoidal. This includes Tanakian categories and super Tanakian. Super spaces is a subcategory of Verlinde, and therefore any fiber functor into super vector spaces will in particular be a fiber functor into Verlinde. And so first theorem is that this theorem of Deligne-Milne holds in this case, but in this case it is due to Ostrich, that if f exists. And well, this theorem is not very difficult, but then there is an analog of Deligne's theorem. So, in fact, so Ostrich asked if every symmetric tensor category in characteristic P of moderate growth can be mapped into var P. And he proved in 2015 that that's true for any finite semi-simple category. If C is semi-simple and has finitely many simple objects, this F exists. So this is a Deligne analog of Deligne's theorem, and this is actually a deep theorem which uses rather deep results from the theory of tensor categories, such as, for example, lifting theory into p-adics and so on, the formation theory of semi-simple tensor categories. Yes?
In your definition of C as var P Tanakian, do you assume C to be symmetric still?
Yeah, always. I talk, these lectures are always symmetric tensor categories.
Because earlier, when we talked about the Z2 grading to preserve the symmetry, the only correct grading to put on thing was not to introduce immunity because it would lose.
That's right. Yes.
So
no.
P is like the good analog of this reasoning. But why does this not break the symmetry assumption having a functor to var P?
This is a symmetric category, var P. Okay. It's a semi-simplification of a symmetric category, so it is itself symmetric. Okay. It is not like having invertible objects labeled by numbers from 0 to p minus 1 and taking braiding q to the ij, where q is a root of unity of order p. So that's different. That example is completely different.
And is C still a k-linear category with k-adic characteristic p?
Exactly, yes. It's a symmetric tensor category. In particular, it's k-linear, so it's a category of comodules over some co-algebra. And it has a tensor product and so on. So this is a really deep theorem. But what is nice is that recently, last year, we were able to generalize this theorem with Coulombier and Ostrich to the case when this finitely many simple objects condition is dropped. So, and I will explain why that's very important, because that enables some rather powerful applications to modular representations of finite group. In Ostrich, 2021, I should say, and this is 2015, is that this holds for any semi-simple, for every semi-simple symmetric tensor category over K, a symmetric tensor functor, fiber functor into VRP. So why is it important? Well, because we can, why was it nice to have a super fiber functor, for example, or usual fiber functor? Because that meant that we could represent a category as representation category of some affine group scheme. In the first case, ordinary affine group scheme. In the second case, superspaces at what was a supergroup scheme, which is the same as a group scheme in the category of super vector spaces. And the third, and in this case also, so if C is VRP Tanakian, then we can form a group G, which is underlying tensor automorphisms of F. And this is going to be a affine group scheme in the category VRP, which means a Hopf algebra, well, all the same things, commutative Hopf algebra inside this category, or we can talk about functor of points, which for every commutative algebra in this category gives you a group. C is denoted by rep G pi 1. So, well, remember in ordinary vector spaces, it was just rep G. In super vector spaces, it was rep G Z, which means compatible with the parity map. And here it should be compatible with the fundamental group P of VRP. So every symmetric tensor category has a fundamental group. For example, if you take category of representations of G, where G is a affine group scheme, then the fundamental group is that affine group scheme. And so for Verlinde, there is also a affine group scheme inside VRP, which is canonical one. So this O, so I will say just O pi 1 is a direct sum over I of Li tensor with Li dual. So you can form this object. This is a commutative Hopf algebra in our category. And this is a certain canonical affine group scheme. And this G receives a map from pi 1. And this means, and also this thing acts canonically on every object of our category. And these are representations which are compatible with this pi 1. I don't want to get into the details of this because this is not very important. What's important is that study of this category can be reduced to Lie theory, but not ordinary Lie theory, but rather Lie theory inside this category. And actually, this Lie theory is, that doesn't mean that we completely solved the problem of classifying such categories, because we have to understand the structure of Lie groups and Lie algebras in the category VRP. And this is a big project which we are working on, very interesting, but very open. There is very little known about this Lie theory. Remember, there is ordinary Lie theory and characteristic P, which is complicated enough. We don't have a classification of simple finite dimensional Lie algebras, for example, in characteristics 2 and 3. Then there is super, which is even more complicated. And now there is this, and this has all the features of super, but also many new ones. It's a very interesting subject, which could be topic of a separate mini course, but probably not now, but in several years where we learn more about these Lie algebras. We are working on this, and this is a very exciting new subject with many interesting problems and results. And we already have some interesting results. But at least this is much more concrete than just abstract categories. That's right, P-1 can have a lot, of course. Right. But they will be representations of this group. So if you understand what this group looks like, and again, if you have a group, okay, so you have Lie algebra, you can consider, enveloping algebra, distribution algebra, things like that, which we do in modular representation theory, and study this category by some explicit tools of classical representations. Okay, but now what I want to do is I want to, so this does not, so not all super-Tanakian, not all Verpi-Tanakian categories are semi-simple, of course, because already Tanakian categories don't have to be semi-simple. Commutative Hopf algebra, so there are two ways to look at it. You can think about a commutative Hopf algebra inside Verpi, or rather inside incompletion of Verpi. And another way is to, well, so what is a Hopf algebra? Hopf algebra is a vector space H together with product H tensor H to H, coproduct H to H tensor H, and a bunch of other things like antipode, unit, co-unit, which satisfy some axioms. And these axioms can be written by diagrams involving tensor products of H with itself. These diagrams make perfect sense in any symmetric tensor category. So in other words, we can say it this way, that there is a prop, it's a MacLane's term, prop, products and permutation category, which is a generalization of operad. So operad only has operations from several inputs into one, and tensor products of those. A prop can have operations which increase the number of elements, like the coproduct. And so we have a prop of Hopf algebras, which contains information about axioms of Hopf algebra. And then a Hopf algebra is an algebra over this prop in the category of vector spaces. But there is a notion of algebra over a prop in any symmetric tensor category. And that's what this thing. You can also think about it in terms of functor of points. So for every commutative algebra in this category, and that's defined in the same way, as I said, but it's a bit simpler notion because only product, we get a group, an honest group, which is a set with multiple operation and so on, which is group of points of this affine scheme over this algebra. Does it answer your question?
Yeah, I guess because for usual case, like K vector spaces, you have K algebra, which is more complex, but now you have an algebra over a category.
Yeah, so this is just an object. It's like, for example, if we had representations of a group, then algebra in the category would be an algebra with an action of this group by automorphism. Here we don't have a group, but we can still talk about algebras. Okay, and so so now I want to discuss some. Okay, so I said that of course such categories, Tanakian categories, don't have to be semi-simple already for usual Tanakian categories, like representations of the group Z, for example. But we do have a complete characterization of Verpi-Tanakian categories. They are so-called Frobenius exact categories. So turns out that one can define, so in usual modular representation theory, an important role is played by so-called Frobenius functor, which is a pullback under Frobenius automorphism of a group scheme, which raises regular functions to power p. There is a similar operation on any symmetric tensor category, which was defined by Ostrich. And that gives you a functor on this category, or rather from this category to the Frobenius twist of this category. Usual Frobenius functor in classical representation theory is exact because it doesn't do anything. It just changes the scalar multiplication. But in this category, it may fail to be exact. And the category is called Frobenius exact if it is exact. And the Verpi-Tanakian categories are exactly those which are Frobenius exact. In particular, this contains the class of semi-simple ones. If I have time, I might explain that later. But right now, what I want to do is I want to talk about applications, representations of finite groups. So representation theory of finite groups is very well developed, and we know a lot about irreducible representations, even in characteristic P, even though not everything. For example, we don't know dimensions of representations of symmetric group. But we know much less about indecomposable representations. That we don't know for very, very simple groups, like the one I mentioned, Z mod 3 cross Z mod 3 in characteristic 3. In fact, this so-called support theory shows that the most complicated things happen for elementary abelian P groups with indecomposable representations. And so here is a problem about indecomposable representations. So let's say V is indecomposable representation. Here it's going to be a finite group. This is already complicated enough to be interesting, but we could take an affine group scheme. It doesn't matter. Representation is finite dimension. And suppose the dimension of V over K is not equal to 0 mod P. So this is a non-negligible representation according to our definition. So then I'm going to take nth tensor power of this. I'm going to decompose it into indecomposables. And some of them will have dimension divisible by P, so they are negligible. I'm going to throw them away. And then I'm going to count those that are not negligible. So define A sub n of V, maybe dn of V, is the number of indecomposable summands in V to the n of dimension divisible, not divisible by P. So this is a finite group. For example, Z mod P to the R. And then I'm going to quote dn of V is going to be an of V to the power 1 over n. In this case, so you can show that, so there is a lemma in elementary calculus, which is called Fekete lemma. So if you have a sequence of positive numbers and an am is less than or equal than an plus m, and an is less than or equal than a constant to the n, then there exists a limit when n goes to infinity of an to the power 1 over n. I will not prove this. This is an exercise in calculus. And in particular, but this clearly holds for our invariants because, so what happens is, okay, so if you have an indecomposable summand of dimension not divisible by P, and you tensor it with another one, the product has dimension not divisible by P, so at least one summand there would have to have dimension divisible by P. And this proves this inequality. And therefore, we have this limit. And so we define d of V equals to the limit when n goes to infinity, dn of V. This limit is at least 1, and this is a real number. But other than that, it is not easy to see anything about this number. For example, it is not clear whether it's an algebraic number or transcendental number. However, here is the theorem. No, these are numbers. These numbers, an of V is a positive integer. So it's bigger or equal to 1. So
increase like at most the dimension of V to the power n.
Yeah, so d of V is less than or equal than dimension of V.
Okay.
And it is greater or equal to 1. In characteristic 0, we don't have, so this is actually, we could take all count all indecomposables. And so in characteristic 0, actually, it's not very complicated to understand what happens. Again, using the notion of semi-simplification. So you will also have some nice, so in that case, it's going to be an integer. But in characteristic P, for example, we could take all summands, not just of dimension not divisible by P. And in this case, I don't know anything about this number, other than that's a real number. So first of all, so we have this green ring. So its basis indecomposable representations. If you have a decomposable representation, you write as a sum of indecomposables and take the sum in this ring. And then tensor product is just tensor product. So Krull-Schmidt theorem implies that this ring is well defined. So first statement is the D from the green ring of G to R is a homomorphism. So if V has dimension equal to 0 mod P, then you can show, then V is a negligible module. So all summands in its decomposition of its tensor power will also have to be negligible and will have dimension 0. So if you have a module of dimension divisible by P and you tensor it with anything and decompose, dimensions of everything you get will be divisible by P. And so this homomorphism, if the dimension of V is divisible by P, V is indecomposable. Yes, a ring homomorphism. And second is that d of V is the summation from I equals 1 to P integer part floor of P minus 1. So d of V is in Z if characteristic of K equals 2 or 3. And then d of V, and it is not divisible by P. D of V, so for indecomposable V, and d of V equals to I equals 1 to floor P minus 1 over 2 Mi times let's call it R, M sub R times R Q, where Q is equal to e to the pi I over P. And RQ is Q to the R minus Q to the minus R over Q minus Q inverse. Simple for P equal 5, d of V equals to M1 plus M2 times plus square root of 5, some integers, Mi, R, and Z greater or equal to Z. Not very well, but not easy to compute them, no. It's not so simple. In particular, this means that they're algebraic numbers. And they're cyclotomic integers, cyclotomic algebraic integers. Okay, and so let me explain the proof. The proof is actually using Ostrich's theorem with myself and Coulombier is very simple. So the proof is the following, that simply this dn of V is simply the length V bar to the n, where V bar is the image of V in the semi-simplification of our category. So we have C is rep G, C bar is C semi-simplification of C. So this is the semi-simple tensor category, and therefore by Ostrich's theorem with Ostrich and Coulombier, there exists a fiber functor from C to ver P. And that's why it was so important to throw away the condition that there are finitely many simples, because this category never has finitely many simples. It has an enormous number of simples. And so, okay, so this is length of V bar to the n. And one can show that this is the same. So this is the same as D, yeah. And one can prove, so it is easy to show that this is the same thing as the length. No, not quite. I mean, so if you take root of degree n, limit when n goes to infinity of length of V bar to the n, one can show, it is not difficult to show, that this is the same as limit when n goes to infinity, root of degree n of length of f of V bar to the n. So when we take f, the length increases, of course, but it doesn't increase too much. So one can show that. And so it kind of, the ratio of this length and this length grows slower than exponential. And so we get this limit, but this limit is just the largest eigenvalue. F of V bar is the sum of Mi, let me call it Ni, Li, then this is the largest eigenvalue, the matrix sum of Ni, Li. So this is called Frobenius-Perron dimension. So this is the sum of Ni, because these matrices commute, times the largest eigenvalue of Li. And this is just IQ. And then we get that Mi is just Ni plus Np minus I. And so, so this shows that, and also this, this thing is, this largest eigenvalue is a character of the Grothendieck ring of the Linde category. That's right. Well, I mean, we have the Verlinde ring, and they are elements of this ring, and they define a linear operator on this ring by multiplication. And this is the eigenvalues of that operator. So there is a character chi from this Grothendieck ring of Ver P, which is Verlinde ring, into R, which sends chi of Li is Q analog of I. And this character here is the D is obtained from that. So D of V is chi of F of V bar. Okay, so that's the application. And in particular for characteristics 2 and 3, this is an integer. So I will talk a little bit more about this next time probably, but then I want to switch to Deligne category. Oh, no. Jordan-Calder decomposition has nothing to do with it in some sense, because this is really about direct sum decompositions. If you have an extension of representations, they define completely different. So if you have a short exact sequence 0 to x to y to z to 0, then x, z, and y define completely unrelated elements of the green ring. It's about green ring, not about the Grothendieck ring. Because Grothendieck ring for such group is trivial, right? So if you take a group Z mod P to the R, then it's every irreducible representation in characteristic P is trivial, one-dimensional. So all the Jordan-Calder factors are just one. So this you lose all information. All the information is contained in this intricate extensions that could be between this one in itself. From that, you can get all kinds of things like this.